All right, so like I said, we're going to dip into Einstein's theory of relativity, and the key words are it's all relative. And so the first thing we're going to look at is time dilation. Now, with time dilation, it's going to remove this. It seems like it's in the way here. For some reason. All right. With time dilation, again, it's all relative. So we're going to start off here with consider a person on a moving cart tossing a ball in the air. All right, so we've got two different ways of looking at it. Now, in our first way over here, it's our first way, and this is going to be our second way right here, is that you have this person, again, traveling on the cart, and they're tossing a ball, and they toss a ball up into the air. Now, from the person in the cart, or what I could say is, in this reference frame, as it's called, frame, the ball only moves up and down, right? So if you're that person who is on the cart and throwing the ball just goes up and down, just like, well, if you're sitting in a car and your car is moving, same idea. You can just toss the ball up and catch it. Now, perspective or relative to, now we have a different situation where we have this observer number two, where watching the same thing, all right, same event, that's the key thing, is that the same event is happening, but yet there's a bit of a different perspective, because if we're looking from observer two, who's this person just watching this happen, well, in this reference frame, that is from observer two, the ball moves up and down just like it did before, but it also moves horizontally. All right, so even though the same thing is happening, depending on your perspective, I guess that's a reference frame, perspective, you can, from this observer one's perspective, the ball only moves up and down, but observer two watching it watches the ball go up and come back down, but also, in this case, moving to the right as that's happening. All right, now, here's something. Note, regardless of your perspective in which the light is moving, because we're going to talk about light. Light travels through space or air with a velocity of roughly, it can change a little bit, but it's fast, 3.0 times 10 to the power of 8 meters per second. So light always travels at same speed, which is 300 million meters per second. Just in case you're wondering, if you traveled the speed of light, you could go around the Earth or go around the equator, I think roughly in less than 2 seconds. So pretty quick. Now, here's what we're into. Something called time dilation. So again, this is perspective. So this is a spaceship, all right? So this is a spaceship moving through space. And all I want to imagine is that you have a laser on the bottom of the floor. And that laser shoots up to the top of the ceiling in your spaceship, all right? Now, a little bit of recall, I guess, from our first unit. All right, so this is just a little flashback, is that V, it's an old little formula for us, is equal to D over T. All right, or I can rearrange this formula where we have D is equal to V times T. All right, now, in this case, because I'm going to use this formula, our D here is the distance from the top to the bottom. All right, or sorry, in this case, I should say bottom to the top. All right, so there's our distance from the bottom to the top. Our V, our speed, is equal to C, which again is the speed of light, because that's I'm shooting a laser, or you can look at it as a flashlight. So that is our V and there's our D. Now, here's where things get a little tricky. Is T our time that this is occurring, is going to be called TS. That's a terrible S, and I really want to write that good. So T is equal to what we call TS, T subscript S. Now, T subscript S here is called stationary time. Stationary time, I guess I'll call it. Because in this frame of reference, or from this perspective on the spaceship, nothing's moving. If you're inside the spaceship, you don't notice that it's moving. All right, so it's called our stationary time. And again, TS is the time for light to travel from the source to the top. Now, what I'm going to do is rearrange or substitute it in my formula. And so what we got here is D is equal to, see here, V, which is our speed of light, times time, but from a stationary perspective. All right. So again, TS is a time measured to go from the bottom to the top. I'm going to keep repeating things a little bit because it can be a little tricky here. We are doing Einstein's theory of relativity. Now, this time, again, is measured by the astronaut who's in the spaceship. There he is right there, or she. Can't tell with my drawing. With respect to the spaceship. So this is basically the spaceship, the clock on the spaceship. All right. Now, let's change it up. Because again, this is one perspective. And as I looked at before, there's two perspectives. So the first one we just looked at in the spaceship is number one. Now we're going to look at this spaceship scenario from number two. All right. So same situation here. All right. Now suppose the spaceship is moving past Earth with a velocity v. All right. With an observer watching from Earth. So where am I going to put my little observer? I guess right here. There's my Earth observer. All right, so here, I'll write that down here. Observing the event, that's what it's called, which is occurring in motion. That. All right, so again, this is the second perspective. So this person here, they're watching everything that's going on here. They're watching this laser being shot from the bottom of the spaceship to the top of the spaceship. But this spaceship is moving, all right? Now, again, I'm going to use my formula here. D is equal to V times T. Now, to start off, I want to make sure I'm going to shrink this down so we can get a better view here. There we go. All right. Now, to start off, when we just look at the distance the spaceship has traveled, it's going to be D. And again, this is for the observer. Who's our person over there that I tried to draw, I guess you could say. All right. Now, the distance the spaceship has traveled is velocity v. I just called it that. So it's v times t, but now there's a little bit different. Tm is moving time because this observer is watching this event happen, but it's moving while it's happening. So we have v times what's called Tm, all right? Now, in terms of this laser, watching this laser, the distance, again, this is the light beam being shot that's going from the bottom of the spaceship to the top. Well, it's moving at the speed of light. And again, the time is being timed by this observer, and to them, this spaceship is moving, which it totally is. All right, so there's our different distances. Now down here, we just measured this, right? The distance from the bottom of the spaceship to the top of the spaceship, if you're just isolating it. And again, that is D. We just did this on our on the last page here. I'm going to go back actually because I forget it. D is equal to C times TS, right? That's just the simple from the bottom to the top from that perspective. All right, so that is, again, C times time, but stationary. All right, now, hopefully you're with me so far. So here's now using this diagram what's going to go on, because I'm going to explain all this in the end. It's very complicated stuff, not easy. But using the old Pythagorean theorem, all right, here's what we got. I've got my hypotenuse there. All right, so I'm going to do that first. So I got, take the hypotenuse and square it. So I got C times T moving time squared is equal to, let's see here, one of the, I guess this side here first. So we go C times T C times stationary time, not moving time, plus the other one there, we got V times moving time. And V again is the velocity of the spaceship. All right, now I can further just do some math here. And well, I square, when you're squaring a term or two terms in there, you square both of them. So I have C squared times TM squared is equal to, same thing here, I got to go C squared times TS squared plus, let's see here, we got V squared times TM squared. There we go. So all I did was just expand there. Now, what I'm going to do here, I'm going to do a little math, is I'm going to divide everything by C squared. Well, that's not going to completely work out for me, but it is going to help my situation here. And so those divide each other out. Those divide each other out. Nah, that's not happening there. All right. So now what I got is I got my TM squared. Just writing down what I got here. Equals TS squared plus V squared divided by C squared times TM squared. All right, now here's what I'm doing. I'm coming up with a formula where I want to relate the two different times, because here's the weird thing is that the times are different even though the same thing is happening. All right, so what I'm going to do is I'm going to move this term over to the other side here, and then I'm going to have to factor out, all right, because I'm going to have this is terms moving over. They both have a TM squared in it, so I'm going to factor out a TM squared. All right, I'm kind of skipping a step here. All right, now there's going to be a TM squared over there, so that's a 1. Then I'm bringing this over here, so it's going to be a minus, and then this times, well, V squared divided by C squared would then give me this term. And then again, over here, I just have TS squared. All right, now what I'm going to do, let's see, I'm going to divide, I'm going to get TM squared by itself. Almost done this part. All right, so I get TM squared is equal to, I'm going to have my TS squared. And what I did was I'm going to divide both sides by this 1 minus. Whoops, I don't have to put that in brackets. 1 minus V squared times C squared. And then the last step to get their formula that we're going to use today is that I'm going to take the square root of both sides. And what I get is time from the person who is watching this thing, the event happen moving, is equal to the time for the person who is doing the event, you should say, or it's not moving in their case. Let's see, that's square root at the top, and then I got square root at the bottom here. And so I have 1 minus V squared divided by C squared. So what is happening here is what I'm trying to explain is if something is moving, the times are different. It's called time dilation. This is a really weird event. So we're going to do a couple of examples. So then another note is this, is that in fact, when you compare the times, the moving time is always greater than the stationary time because of this formula, the way it works. Because down below here, this can never be, well, it can never be negative. So it can never be less than 0 inside here. Now, again, Tm is measured by the observer from Earth or from whom the event seems to be moving to them. And v, again, is the velocity of the object in which the event is taking place. All right, so what we have here is what's called time dilation. So I'm going to keep, I'll read off this, but the slowing down of time in a system as seen by the observer in motion relative to the system. That's wordy. Again, we're going to do a couple questions here, and hopefully I can explain a little bit more. But again, here's the key for Albert Einstein, is time is relative to the observer. And there is no such thing as absolute time. So a second is relative. A second for me sitting in my at my desk here is different than a second for somebody who's traveling on a spaceship moving very quickly. All right, so that's a little bit different concept there. Now, the interesting thing about Albert Einstein, he was called a theoretical physicist, is he never worked in a lab. He just thought of all this stuff up in his head, believe it or not. All right, so now we get to a couple of questions. Is that, first of all, here's our equation. Tm is equal to Ts, again, over the square root of 1 minus v squared divided by c squared. Now, as I mentioned, in short here, the bottom can't be less than 0 because we're taking the square root, right? You can't take the square root of a negative number. And what that means in the end, a little bit of math thing is Einstein came up with the theory, and it has been since proven since he died, that everything that he said is true. He never saw that this stuff was true for real. He theorized it was real, but they actually have proved it is real. But no material thing can have a speed equal to or greater than the speed of light. So you cannot go faster than the speed of light. And the other thing that this formula proves is that you cannot go back in time. Time travel is impossible. So for all of you people who watch all those movies, sorry, but it's not happening. All right, now let's get to a question. So we start to figure this, kind of explain to you what's going on here. So example 1. An astronaut is sent on a voyage on a spaceship. He returns in 10 years as recorded on Earth. How much will he have aged if he was traveling at a speed of 2.7 times 10 to the power of 8 meters per second relative to Earth? All right, so here we go. All right, so again, we're going to use this formula. Tm is equal to Ts divided by the square root of 1 minus v squared over c squared. All right, now, a couple of variables. First off, speed of light, always the same. That's our c value, which is equal to 3 times 10 to the power of 8 meters per second. All right. That doesn't, now this spaceship, that doesn't change. The spaceship has an incredible speed of 2.7 times 10 to the power of 8 meters per second. All right, now we get to this, the difficult part. Tm and Ts. These are the tricky ones. Now, which one are we trying to find out? Now, this astronaut went on a voyage on a spaceship. So here's Earth. And here's our spaceship at a velocity. Now, when we're on Earth, we measure the time of this spaceship. The time is recorded on Earth. Well, relative to Earth, this thing is moving, right? And so our Tm is 10 years. All right, because what we're watching happen is this person traveling. We're watching it happening, and that spaceship is moving. But what we want to know is the astronaut, what time do they have on their watch? Because to them, they're not moving. They're on a spaceship. Just like you're sitting in your room right now, believe it or not, you're moving, whether you think you are or not, because the Earth is moving. But relative to you, from your perspective, you're not moving. I feel like I'm not moving here, but the Earth is spinning at an incredible speed, and we are moving. All right, so now I'm going to substitute into my formula here where TM is 10 years. So TS and TM are in the same units. I should mention that. All right, is equal to TS divided by 1 minus, and again, V squared, we have, 2.7 times 10 to the power of 8, and that value is squared, divided by the speed of light, which is 3 times 10 to the power of 8. And again, we square it. All right, so I'm running out of room here, but a little bit of math is I have my 10. All right, so TS. All right, so let's see here. Down below, I'm going to have a 1. All right, so I'm going to do some bit of math here, and let's see here. So I got 2.7 times 10 to the power of 8 squared. All right, and then divided by 3 times 10 to the power of 8 squared, and I'm getting 0.81. All right, now let's see here. Go up here. Sorry about that. 10 is equal to, I have TS. And let's see here. I subtract from 1 minus 0.81 and then take the square root of it. Let's see here. Oops. And here's what, hold on here. Okay, yep, I got it. So that is 0.43, 2 decimal places here, 44, I guess I should do. We'll go 4.36 or 0.436. All right, now I got a fraction, a number equaling a fraction, so I can just have a fraction equaling a fraction. So I have cross multiply, so I have 1 times TS, which is TS. And then I go 10 times 0.436, which ends up being 4.36. And again, TM and TS have to be in the same units. Years. So here's what this means. This is really weird. It's called the twin paradox. So if you had a set of twins and one of them stayed on Earth and the other one jumped on the spaceship and traveled at this speed, and say they were 10 years old when this started, after 10 years on Earth, the one twin would be 20 years old and the other twin would get off the spaceship and they would only be 14.36 years old. So what happens is with time dilation is if you move faster, time slows down. And so you don't age as fast, which is a really weird concept. All right, so that's called time dilation. Again, different little concept to go after there. All right, so a little, and here's how it would affect your age. So we get to example number 2 here. Is we have an astronaut on Earth, an astronaut's heart rate is 120 beats per minute. All right, now she travels into space in a spacecraft capable of reaching super high speeds. Determine the astronaut's heart rate with respect to the clock on Earth as the astronaut flies by Earth traveling at 0.5 speed c, which is half the speed of light. All right, so again, I'm going to throw down my formula here. Whoops, I like to use a different color for that. So I've got TM, our moving time, is equal to our stationary time, TS, divided by, again, 1 minus V squared over C squared. All right, now our V, our velocity of the spaceship is 0.5 c. All right, now c is, well, that is the speed of light. Again, that ain't changing. 3 times 10 to the power of 8 meters per second. Now let's get into TM and TS here. TM and TS. Now, we have a person. They have 120 beats per minute, right? So 120 beats per 60 seconds, I should say. All right, which means if I divide those, you get 2 beats per second. Now, I could flip that around and say that, therefore, it takes, if you do 2 beats in a second, it takes 0.5 seconds per beat. All right, so that's pretty crazy. Now that's our time frame there. Each beat of our heart, in this person's heart, is 0.5 seconds. So now I have to decide, is that a stationary time frame or is that a moving time frame? Now the key words here is on Earth, the astronaut's heart rate. So that is my stationary time is going to be 0.5 seconds. Because on Earth, they're standing on Earth, they're not moving. But now this astronaut is going to jump onto the spaceship, and we want to know with respect to Earth's clock. So on Earth, this spaceship's going to be moving. That's our moving time. How many beats per minute does it take? All right, so again, I'm going to substitute into my formula here. All right, so we have TM is equal to, well, I have a 0.5 here because that's how long a heartbeat takes. Underneath here, I have 1 minus, I'm going to have a 0.5 c as my velocity, and I have to square it, divided by, well, c squared. All right, now, let's see here. So I got a 0.5 on top. That's my heartbeat, how long it takes. Let's see. So on the bottom here, let me see. I square the c. Those c's would cancel each other out because I have a c squared in the bottom. This c would be squared. So all I hear is I'm going to have 1 minus whatever 0.5 squared is. 0.5 squared is 0.25. All right. Now, let's see here. I take my 0.5. I'm going to do down the bottom here. I'll figure it out. I got 1 minus 0.25, which I know is 0.75, and then I square root it. I'm getting 0.866. All right, and so that means I take 0.5 and I divide it by 0.866. And before it would take a heartbeat 0.5 seconds. Well, now time is being slowed down because they're moving, and I'm getting 0.58 seconds. Now that is what's called the period. That's how long it takes to complete 1 heartbeat. All right, so what I want to do is find out the frequency. So hopefully you have done a little grade 11 physics where the frequency is 1 divided by the period. And so if I do 1 divided by 0.58, I'm trying to find their pulse here. I get 1.72 beats per second. Whoops, beats per second. Now, if I times that by 60, because remember, this person had 2 beats per second, but time is slowing down because this person's moving. And now they're just down to 1.72 beats per second. And so if I times that by 60, I end up with a pulse rate, because we're doing pulse per minute here. Pulse is now equal to, let's see, I take 1.72, I times 60, I get 103.45 beats per minute. So again, their old heart rate when they aren't moving is 120 beats per minute. But because time when you're moving slows down, now they're 103 beats, 103.45 beats per minute. And so they're not aging as fast is what's happening when you move. Now, they've actually, whoops, stop presenting here. This has actually been proven in real life. Now, what they do is there's certain particles in the atmosphere that exist, but they only exist for like a billionth of a second. All right. So there's particles that only exist for a billionth of a second. So what they do is they speed these particles up, and they found out that these particles don't last for a billionth of a second. They start lasting like a millionth of a second, which isn't a whole lot of time, but yet it proves that if you move quick, time slows down and you age more. Now, you have to be going extremely fast because they've also proven this with fighter jets and atomic clocks, clocks that mark billionths of seconds, and they get jets up traveling, faster than the speed of sound, which still relative to light is slow, but there is differences in the clock. Now, the crazy thing is that if they fly east, the clock slows down, and if they fly west, the clock slows down. But the clocks are not the same, even if the fighter jets go the same speed. Anybody know why? Well, here's why. Because the Earth spins. So when you're traveling with the Earth and it's spinning, relatively, you're not going that much faster. Then, if you're flying your jet and the Earth is spinning this way, then you're definitely covering more distance, and relative to Earth, you're going faster. So if you fly against Earth's rotation, you seem like you're even going quicker than if you're flying with Earth's rotation. Now, again, you have to be going at extreme speeds. So unfortunately, somebody who's, say, an Air Canada pilot is not going to live longer than the rest of us because they just don't fly that much faster. So, but it does make a difference.